My name is Francisco Martinez. Today we're going to go over a case comparison against some GeoStudio tutorials, some typical tutorials you can actually download from their page for 3 different comparisons. We're going to first compare against their Sigma W. They have a tutorial called Stress Bulbs Beneath a Tank. We'll go through the procedure in the Midas GTS NX program and compare the results. We'll then do a jump to another one of their programs called SeepW. They have a tutorial called Seepage Through an Embankment. And we'll go through how to do that again in GTS NX for 2D. And then lastly, we'll go through one of their last programs called SlopeW. We'll do a comparison for slope stability analysis through the strength reduction method. So we'll jump right to it. The first tutorial we'll cover will be a model called Stress Changes Beneath the Ground of a Tank. I actually sent everybody the files this morning. If you did not receive them, I would gladly send them to you again. So in this tutorial, basically what we're going to be looking at are just the pressure bulbs beneath what would be considered a tank. In this case, what we're looking at actually is considered a symmetric model, and so we can model this almost as a 2D, but in reality it's called an axisymmetric file. What that means is that if your model, in this case we're looking at a tank being round, is completely symmetric, you can actually just simplify it. You can take an axis of symmetry and just take almost like a slice, and the program can then give you results as if you were looking at the whole model. So in this case, what we have here are the dimensions of our model. The tank will be in the top left corner, as we saw with the load distribution being there. And what we see is that we have 2 main soil layers, which we're going to model into the program. So for starters, the program allows you, when you start a file, allows you to choose between 3 model types. So that's one big difference. We can work between all 3. So in this case, as I mentioned, because it's a symmetric geometry, we're going to do the axisymmetric model. And you can also then choose your units. We're going to be working with SI units. So I'll actually open a starting file so we can go through this step by step. The starting file that I send everybody has the materials defined and the geometry in place, but it's very easy, and I'll show you in the slides how to go on Wamba, either draw it or you can directly just import it. So the first thing would be to define the materials. In this case, as I mentioned, there's only going to be 2 materials, and the tutorial for Sigma W did not have any porosity properties for this particular file, so it's just going to be straight elastic properties. All we have to define are the elastic modulus, the Poisson ratio, and the weight. So to do that in GTS NX, in the starting file, you would go to the Mesh tab. We have on the very first section, well, it would be the material command. And from here, as we saw, as I mentioned, the starting files already have the materials defined, but to create a new one, you basically just go to create. We have different kinds of modeling you can do. You can even do specific materials for other advanced seismic analysis, like 2D linear equivalent. But in this case, most of the cases we're going to be doing is isotropic. We would select from the model type. These are the constitutive models database that we have in the program. And you can see that we have some pretty advanced ones, like soft soil creep or UPC sand for liquefaction. But for these tutorials that we're comparing with GeoStudio, we're going to stick to elastic, and further ahead we'll do more column. So we would select elastic. If we don't want to have any consideration of the porosity, we can actually activate this as a structure, and this tab goes away. So we're going to stick to the general tab. And this is where we manually just type in the values for elastic modulus, Poisson ratio, and the unit weight. And you would just do apply every time a new ID would be created. You would give it a new name to separate the materials. And if we inspect them here, we're basically looking at these 2 that we have the material values in the tutorial explained. Once we've created the materials, we have to tell the program how these materials will be used as a mesh. So for that, we would go to the property window. In this case, what we're going to do is, this is considered to be a 2D element, but it's a subtype axisymmetric, and that's important because when the load is being applied and the results are being interpreted, it has to consider that it's actually a 2D render of a 3D model, not just straight 2D. So what we would do then is go here to property. As I mentioned here, these two have been created, so we would just go to create 2D, and we would select which type we're working with. As I mentioned, we're doing axisymmetric. We select the tab, and all you would have to do is just select the material that you want and give it a name that matches. This is going to allow you, when you're meshing, to select the two sets. So you select both and give them the according material properties. So now you have your material and your properties. You would then proceed to create the geometry or import the geometry. The program has very similar commands to what would be an AutoCAD, and it also has a grid that allows you to draw on it directly. Now you can change these dimensions of the grid. In this case, the width of the spaces has been changed to 1 meter spacings, and you can also make it larger or smaller in sense of like how far the grid goes. In this case, it's a 40 by 40 grid. Once you have the grid on, you can directly go to the geometry commands and do all kinds of geometries. So you can, in this case, directly count and draw a rectangle, or you can import by coordinates by this method of two corners, the first corner being the origin and the last corner being the opposite end, which would be a 38 by 25 box. And then you could proceed to draw directly on the program. So I'll show you this as well. So let's just say we have this geometry, but I'm going to just deactivate it, which I have here on my work stream. I can activate and deactivate anything. And then here are the commands for what I was mentioning, the grid that allows you the work grid. So we see here we have the grid. I can also activate these basically axes to show me the origin. And if I wanted to change the dimensions of the grid, this is where I could vary that and give it a different size, different spacing. Now again, I'm working with these units, but you can easily go to other units within the program. So once you have your grid, you would go to the geometry tab, and you can start, as I mentioned, either inputting coordinates or just drawing directly. And you can easily just draw different lines along the grid to match whatever it is you're trying to draw. And once you deactivate the grid, you would see these lines. If I ever want to undo anything, I can select from here. So I'm going to undo these and just activate my original or my starting geometry. But if you follow these procedures, you would be able to either draw it manually or type in the coordinates, whichever is more comfortable. Once we have the initial geometry in place, either you imported it or you drew it in, the next steps would be to prepare it for meshing. In some cases, you can just go straight to meshing, but we want to, in this particular model, match the mesh shape. And what we can do within Midas is use this command called size control that allows you to get very specific about how the nodes themselves are going to be distributed prior to meshing. So we see here that we have some cases where some of these lines have 1 meter spacing. Some other corner has a 2 meter spacing between nodes. These three areas have a smaller distribution, a 0.5 meter spacing. And then we see here that this last one is what's called a linear gradual spreading. So it starts off at a certain size and then it gradually gets bigger. So we'll go through all those three just to show you the versatility and how much control you can have on the meshing. So we go back to the mesh tab, you go to size control. So these have a 0.5 meter spacing. These have a 1 meter spacing. This one has a 2 meter spacing. And then from here I can actually change the method. We're going to do linear grading. I'm going to select these two. You can see there's actually a directional line, and I want to select the third one. But if I select it now, given the orientation of the geometry, the program automatically assumes a clockwise direction. So since it's in the opposite direction, but I actually want them to have all the same distribution, I can unselect, and then I have a second option to select lines, reverse to the original. So then from here, my starting distribution is 2.5, and it eventually grows to 2. So we can see that also linear grading distribution. So I've now predefined some conditions for my mesh, and I would be able to then proceed to mesh and get this, what we see here, just as a general idea of these gradual changes of mesh sizes. So we would select overall geometries. In this case, we have two main layers. So the bottom layer and the top layer are the two main soil properties. We're going to use quadrilateral elements, and we're actually going to activate the higher order element feature, which is creating nodes in between the elements, almost like subdividing the elements. And that's good for slope stability, and it's good for cases when you have a high displacement or high deformation mesh requirement, like consolidation perhaps. Like if you expect a high deformation, you can help the program out by giving them some extra nodes. It's one way to think about it. So we can proceed now to mesh. In this case, I'm going to mesh 2D. I'm going to select area as my filter, or as my option. I select the top. I'm going to give it a size of 1, select the property to be the upper, and I can go here to the advanced options. It's this triangle here. I can select what kind of element type. We mentioned quadrilateral, higher order element, and I can just go ahead and mesh, and then I would repeat for the bottom. And we see now these distributions have been, regardless of the overall size I gave it, the dimensions are going to be skewed to match the size control, which I can then deactivate from my works menu just to make it a little cleaner. So we see here now in the work tree under the model tab, we have our meshes, we have our geometries that we've now created. So we can then proceed to apply the boundary conditions, which the program can do automatic. It'll recognize all the boundaries, as well as what would be the self-weight and the load. In this case, we would do a pressure load, axisymmetric pressure load, as we're considering a model that's in reality 3D, but we're modeling as 2D. So we would go ahead and just go now to the next tabs. We're done with meshing. We would then do here on the boundary is our constraint. As I mentioned, we can just do an auto. If you notice, there are symbols in between what would be the edges of the element. Since we use higher order elements, as I mentioned, there's nodes in between each of the divisions, and this is why we have that representation. And then you would have here the pressure, all the loads you can apply. Axisymmetric, you would select the elements you want. We give it the value, and we can actually preview it. In this case, it's correct, it's going down. And we would then be ready finally to create an analysis case. This tutorial is very simple, so we're just doing a linear static analysis. So we would go ahead and proceed now to analysis, general. We select from our list here all the solution types you can do. You can see we have more advanced ones, and we'll see later a construction stage analysis as well as a C-pitch analysis. But we can also do all kinds of seismic analysis, slope stability analysis. So we just give it a name. We can drag and drop conditions that we want or deactivate. In this case, we just want everything activated. And then we would be just ready to perform the analysis. I'll go ahead and just jump right into one that has the results open. Or I'll run it real quick just to give you an idea of the time. It doesn't take long for these simple 2D cases, but I'll also just show you here the final results. What we have then are, since there's only some kinds of structures in place, or only some kind of elements, we have displacements and we will have like the stresses. But if you had other kinds of elements like beam elements or shell elements, you would see the grouping by type of element. So we could then start comparing results. So we see here this took less than 2 seconds to run. The tutorial for sigma W specifically looks at stresses, vertical stresses. In this case, the Y direction is the vertical stress. So we were looking here at the pressure bulb. We can actually use other commands like iso value surface to isolate the range of values we want to see. So in this case, we want to see the stresses up to a certain range. So to do that in the program, we see here that the colors are actually a little inverse. I can easily go to my, what would be legend, and go to reverse. And then I can use other commands within the results like isosurface, as I mentioned, and activate by certain range. So as I mentioned here, we would give it anything up below or anything. In this case, it's the negatives. This in reality is we were looking at the higher values, but the negatives in the down direction. So we're looking at the range from 5 to 40 of this pressure bulb. And then the other result that they look at specifically would be the displacements, which we can actually activate as the max. I could also change the units to centimeters and millimeters. So we're looking around 76 millimeter maximum total displacement. As we're looking here, deformation can also be activated or exaggerated. Other things that we can look at would be the lateral displacements at a certain section. We can even include diagrams or extract the results directly. In this case, we're extracting results and graphing them since it's something that was done directly in the other tutorial. So to do that in the program, you would do a cutting diagram would be when you draw it directly in the program. Let's do the lateral displacements, and you just have to create a line along where you want this and which direction you want it to be extruded or shown. In this case, this is how we could see specifically a diagram there. The alternative, if you want to graph it, would be to extract the results. In this case, you would choose which results you want to do, specifically lateral displacements, and you can just select the nodes, create a small rectangle to select the nodes you want, and go to table. And then from there, you can directly do something like a depth by displacement, export to Excel, and the format that the graph for sigma W was in a very specific, I guess, axis. So in Excel, we were able to match that as well. So here we're looking directly now at comparing sigma to our pressure bulb model. We see that in their tutorial, they mentioned the final displacement of 76 millimeters, which is very close to what we see in our program. And then they also do the pressure bulb isosurface, which again matches what we see in our program, as well as the lateral displacement distribution with depth that we graphed here. So this is a one-on-one comparison for this tutorial. Now we would do a quick case study. The upside of what we see now is that while sigma W is maybe limited to 2D or axisymmetric, within GTS NX you can actually also go to 3D. This is a study of water tanks for a water treatment plant in Colombia from one of our clients. We're looking at the side view and the isometric view. Their main issue was that their soil is very, very soft. They're in clay. So we see here some of the properties of their clay layers. So they went through a construction stage analysis, everything through the excavation, the installation of the tanks while they were empty, the reinforcement of the ground, and then finally the load of simulating what the tank would be full. And they did a 10-year, 20-year, and 50-year consolidation analysis. So we see here we're looking at displacements for the different stages, the excavation stage. Then we jump to the fourth stage, which would be with the tanks being full, what they consider the load. And we start to see here now the uplift and the sinking. So it's sinking already around 10 centimeters with the initial load. And then we're looking at this consolidation process. 10-year, we're looking at it sank around 11.5. 20 years, it sank around 12.3. And then 50 years, maximum sinking is around almost 14 centimeters for this particular distribution. So these are some of the analysis that you could not be able to perhaps properly model in a 2D simple case, specifically when you have a higher distribution of all these different geometries to consider. So that's the first case. Now we're going to go to seepage. We're going to compare a seepage through an earth embankment for seep W. In this tutorial, we're going to do a 2D analysis. And we see here we have basically an embankment. The water would be on the left side, and we're going to vary the porosity properties of the core to see how this is affecting the seepage from left to right. So this is, again, a direct comparison to one of their tutorials. Here are the dimensions of the embankment. And we see that we have like a toe at the bottom right. So different to last time, we're actually now working on a 2D, not axisymmetric case. But you, again, when you start a new file, you select which model type you want to work in. And the definition of the materials would be similar, except in this case now we're actually going to have to define particularly unsaturated properties of our core and our shell layers. So similar to what we did last time, we would go to define the materials, except this case we also work on the porosity tab. So we go to Mesh, Material, Create Isotropic. We're selecting Elastic again. We would leave this off. We would define, these actually are going to be the same for all the materials as we see over here, these same material properties, the general properties. The only thing that we're going to vary are the saturation properties. So within GTS NX, you would go to the porosity tab and you would give it information about permeability, if you want to be drain or undrained conditions, as well as what would be the saturation properties. So to define these, you would just go to Add Individual. You see here that we have different types for selecting or defining these properties. The easiest and most common one would be just to user define. And so what you end up doing is you have, as I included in this morning files, just these Excel sheets that you can directly copy paste into the files to match the properties that you're working with. So you will also see that some of these dimensions go lower than, or the number of units here are represented by 0. Even though they are being represented in the graph, they just don't necessarily show in this table. So you would define basically we have 3 main core saturation properties we're going to be using, which is the 3 we have here. And then we use an additional one for what would be the toe in this case. Once you define the materials, you would then just go and tell the program these are going to be used for 2D meshes. When you work on 2D straight, you just do the plane strain. And all you have to do again is match a name to the material property you're working with. So we have 4, which is what we've done here. The procedure would then be for geometry. We have the starting geometry, but you can use different commands. There's also what's called the polyline. You can keep adding on additional locations or drawing within the same segment, the same line to create your final geometry. And then lastly here, they do additionally some new segments to create the core. What you want to do at the end would be also to use the command of intersect, just to make sure that the program recognizes all these divisions when you're selecting geometries to mesh, which would be this command up here. So we have the starting geometry, we have the materials defined, again, which was drawn from the grid and using these commands as well as the intersect. We would now be able to proceed to mesh. We would do the area selection. So for the core, what we want to do is use just a smaller size. In this case, we're not going to use size control. We can just change the size of the elements by region. So we would have the initial or the general core with this general property. And then we would have meshing the 2 shells. We would just give it a different name. And we want to give it a bigger size. We'll do 1. We see the automatic gradual change of size to match. We'll do the toe. We'll leave it as 1. And then what we want to do is mesh the core with these other properties. So I would just deactivate, select that area again, go back to the other size of 0.5, and give it the other saturation properties. And we'll do it one more time for the 100. Once we have our mesh created, we would proceed to then define the boundary conditions, the seepage boundary conditions. In this case, we're going to tell the nodal head the height of the water would be on the left side 8 meters. We're going to give it a review boundary condition on the right side, which is basically telling the program this is going to be where the water comes out, and we want it to calculate based on the other seepage conditions and the saturation properties. And then for the toe, we're actually going to give it a nodal head of 0. So then we would be able to proceed now. We're going to go to this tab, the seepage tab. We would go here to then these boundary conditions, nodal head. We see we have different methods of applying it. We can actually select by specific nodes to apply the head, or we can select an edge, a total geometry. So we would then go here to, this would be our 8 meter boundary. We would then select again, I'll change the format to by nodes. This would be the toe, which would be at 0. And lastly, the review, which would be on this end. So we've now created all the boundary conditions, and we can go ahead and go into the analysis case. We're going to create 4 analysis cases to match what we saw in the tutorial for SeepW. The first case is the original core with no toe. The second case is the same thing but has the toe condition turned on as well as the toe seepage condition turned on. The third case is we're going to replace the core with the other material property 10x. And lastly, the fourth case, we would run it with the 100x. So we would go to Analysis, General, Analysis, General. We select here, all these are seepage steady state, although we can also define time conditions and functions if we wanted to do a transient. So we see here now, we want to drag and drop to deactivate some sets that we don't need yet and activate others that we do. So this is case 1. We would just go to Apply. If we use Apply, then it stays, the command has been created, but we can go ahead and proceed to make the new conditions. So we will now activate the toe, 2. We would then go to 3, deactivate the general core and activate the other property. And lastly, 4, replace this one again with the 100 times property. So we see here now we have the 4 cases created. We would go to Perform and run this analysis. Again, I have the model finished. So we're looking here at the 4 cases results. We see that the program has grouped them accordingly, and we could see results like the total head. We could see the change of this over time based on the different core properties. We can also look at the pressure, pore pressure. But the program also has other results like hydraulic gradients or seepage flow that we can look at, more advanced results. Within that, the program also allows you to see the surface of the water level. You can select here pore pressure and give it the range of 0 to plot it. And you would be able to see that change of water level through the different cases. So we see here with this more permeable core, it goes much lower. So we were able to compare these results. We see this also took a very short time to analyze. We were to compare these results now to the Sigma W or SeepW. We're going here through the 4 cases results. We see we have a very similar distribution for the cases, the initial case down to the last case where the water it's almost at the very top of bottom of the core, already starting to hit the lowest end. So we see here also this is the third case, which would be over here. So we see we also have a very similar distribution. To contrast that to a 3D case, we have here a project of Bugam Dam in South Korea. This was a construction stage analysis of the dam, as well as considering the pressure when the level is full at the last stage. And so we can get stress results, what we call semi-coupled analyses. You can go through these construction stages and start considering in your stress conditions like seepage conditions, like hydrostatic pressure. But then you can fully jump into what would be just the pure seepage analysis, where you get results like the head, hydraulic gradient, flow rates, or even including a flow line. So this would be the dam itself. And so we could look at the, as I mentioned, construction stages for the stress part as we're going through the whole process. But then we can also look at other, if we were just doing a pure seepage analysis, considerations like seepage head, hydraulic gradients, and such. So that was the case for seep W, and now we can proceed on to slope W. So in this case, we're going to do a slope stability analysis. The main method for this in finite elements is the strength reduction method. We see here the dimensions of our slope. It's a 20 by 50 by 10. What we're going to vary actually in this tutorial, that slope W, what they do is they reduce the cohesion and friction angle incrementally of the initial condition, and they see how the slope factor of safety is being reduced. So that's what we're going to do in our case. Again, we're going to be working on a 2D case. So we see here the material properties defined, the general tab, everything stays constant. But now we're actually using a model called Moore column. So this is a nonlinear model, and we see we have a new tab now that allows us to define the properties for cohesion and friction angle. So we will define for these 6 materials, as we mentioned, we will basically just be switching between these properties as we are gradually reducing the nonlinear properties of the soil, and see how this is decreasing the stability of the slope. And in the end, actually, I'll show you that the program does have, for 2D, the ability to do slope stability by another method called strength analysis method. It's a hybrid method with the limit equilibrium, where you would define your grid and your arc similar to like limit equilibrium. So we start off by defining the materials, and again, the property would just be plane strain 2D. So we have here the starting file. I would go to to mesh, material, create isotropic, and this time, as I mentioned, we're selecting the Moore column, and we see we have a new tab. So the general tab would be the same, and you would just apply or define your friction angle and your cohesion. So as you're getting into the more lower end of the list of considered models, you see that these nonlinear tabs become more and more complex. The most commonly used nonlinear considered model is Moore column. So you have all your 6 materials defined, as we mentioned, this being the strongest, this being the weakest, nonlinear properties wise. And then you would just define the properties telling it we're going to be using these for 2D. In this case, again, the geometry could easily be traced or drawn on the grid. You can just go ahead and draw with, I guess, your polyline and follow the dimensions, or input by coordinates, whichever you prefer. And then you would be ready to mesh. So in this case, it's going through the steps of getting the grid in the right size and dimensions, and then going through the input locations. But lastly, now we're going to go ahead and start meshing. So everything here is going to have the same size of mesh of 1 meter, and we're going to, again, activate the higher order elements since we're doing a slope stability analysis. And we'll just repeat this 6 times for our different materials. So we go to 2D, area. We give it one size. We go to advanced to activate the higher order. For this case, it doesn't really matter if we're doing what kind of element. We'll let it choose both triangular and quadrilateral. And we'll just go through the different materials. So material 1, we select from the next list. Material 2. So the color will stay as the original mesh set, but you'll be able to see in the worktree that you actually are creating these different mesh sets. If I go over here and expand my mesh sets, we see we're down to the third one. And if I deactivate one, the other ones show up. So then we will proceed this to all the others. 4, 5, and lastly 6. So we have we have all our mesh sets created. We would then proceed again to automatically create the boundary conditions and apply it. In this case, the only load is self-weight, which is in the y direction, gravity being vertical for a 2D case. So we go now here to static slope analysis, and we would create the automatic boundary condition constraint as well as the self-weight. And we then proceed to do the definition of the analysis cases. So in this case, we're not actually going to make 6 separate analysis cases. What we're going to do is we're going to use the construction stage analysis, and in each stage, change the material property. It'll retain the stresses from the previous stage, but now have the new material property. So this is a little bit uncommon. It's not kind of realistic. We're just trying to match what was created by the slope W. In reality, you couldn't change the ground uniformly for a whole slope in a single step. You would have to somehow reinforcement or treat it. But for the sake of this study or this comparison, that's what they did. So we're just going to incrementally lower the material property of the same soil condition through these stages. So what we'll see here is that we'll have, in the construction stage analysis, you have 3 windows now. You have everything you've created, the middle, which is what you want to be activated for this stage. And then we'll see later that we can actually usually want to clear displacement, so all our future results are purely based on what we're applying as a stress. And you'll see you have commands options here for stages to activate the slope stability by both methods. If you define the boundary condition for the other method, the arc, which I'll show you later, you can also consider that factor of safety. So what we end up doing is, as we're proceeding, we're just deactivating one set by dragging and dropping it, and then activating the new one, and again telling the program to run a slope stability analysis with this new condition, and so on and so forth. Every time we deactivate the previous one and activate the new one for each subsequent stage, activating this option. So I'll show you how to do that. That's actually finished. So we would go to, in this case, we first have to define the construction stages. We go to stage set. We can select from many kinds of construction stage analysis. For now, we're sticking with stress. But if you want to do something like the coupled, considering the seepage conditions, you can do something like stress seepage slope. So we add it. Once we created it, then we can go on to define it. So we see here we have all our mesh sets. We're going to start with 1, apply the boundary condition and the load, and we're going to clear the displacements. And then in the subsequent stage, everything that I've already activated stays activated. So all I have to do now is tell it that for this particular material, I want a slope stability analysis. Now I can go on to a next stage and deactivate the original soil. We see here that it's no longer visible. It's been deactivated, but I can now activate the new condition or the new material and give it again a slope stability analysis and proceed in the same order for the rest. So on and so forth. Until we get to the last one. So So once you've done the analysis stages, you can go to General and tell it that you want to run a construction stage analysis. You would select from the list. In this case, we only have one set. You give it a name, and it's important to tell the program. In some cases, we do the semi-coupled, and some stages are initially C-pitch analysis. You want to tell it when to start the stress analysis, and if you want to do the K-naught condition. And once that's done, then you would just go ahead and run it. And again, I have it already done. We see here that our results are in the post-processor, and we have for the sequence. And we can see that initial factor of safety being 1.5. Once the material has been reduced properties, it drops to 1.29, then 1.19. And eventually it gets very close to failure, to 0. So we can expand these results. Now this is a slope stability analysis, so all your displacements are considered to be already kind of failed in some respects. They're exaggerated. What you really mostly would be looking at would be your plane strains, your max shear, which for the slope stability analysis is your surface failure. If you wanted to do just the regular displacements or stress analysis, you wouldn't look at, you see you have two sets of results for each case, the SRM and the regular. So you can just look at your regular displacements for the stress analysis. And again, for the SRM, you're looking at your factor of safety, but this is be focused on the slope. So you see here we're looking at a 2-meter displacement, which is not necessarily realistic, but it's under this kind of analysis, what you see. So we see here the summary of the gradual decrease of the factor of safety as we're replacing our materials. And then here's the comparison with slope W, which we see very similar here. It starts at 1.5 and gradually drops to almost below 0 or below 1. If we look also to other results like the shear stresses, we can also see that it's a very similar distribution to what we're looking at, something like slope W. So lastly, we'll do a 3D case study. This is from another client that we have, HMB in Colombia. They do a lot of hydroelectric water dams, and in this case they had to do some bench cuts on a slope to make room for the housing some of this equipment, machinery equipment. So this is the initial geometry, which was, as you can see, the terrain is very realistic. This was used with one of the tools we have, a terrain geometry maker that allows you to use topographic maps to create your surface or your initial file. So we see here the initial meshed file and the final excavated file. We're looking at here at results for displacements, initial and final. The program allows you to easily do other things like create vectors in your output or isolate, in this case, the failure surfaces by range or value, which we saw in the first model. So it's very versatile, but also very handy for the 3D cases. So in conclusion, we see that GTS NX and Geostudio give the same results when we match the conditions. However, the GTS NX has a very practical application that you can actually jump to 3D, even if you have a 2D mesh file. But this is kind of typically if it was a uniform 3D case, which might not be always the case. In reality, 3D models, or you do something in 3D because you have uneven or unsymmetrical considerations. So for that respect, the GTS is also very strong since it allows you to import any kind of CAD file, be it volume, being solids, surfaces, or lines. So you can really push the boundary, as we saw in some of these cases, for the complexity of the 3D analysis you're doing. And lastly, you can actually jump in between kinds of analyses within the what we call coupled analysis. With the Geostudio, it's a suite of softwares. You have to work within one or the other. I believe you might be able to export results. I'm not entirely sure which are compatible with what. But with GTS NX, you can do it all in the same one. I'd like to just conclude reminding everybody that next week, Don Doxson and I will be having a shared webinar, and we'll go through a case study for a real application project. I think it goes through several softwares, and the final result would be a 3D retaining wall in GTS NX, but it'll start from something 2D. That one would be actually a bit longer. I believe Don Dodson is going to go a little bit more into detail since it's a real application for AMIC. and he'll go into the details of where the project started, where they are now, and what they hope to compare once they have the 3D results. But so this is the conclusion, but I would like everybody, if they want to email us questions, let me add here at the end. Sorry, I forgot to put. So you can email me any questions you have directly at this email. And I'd be glad to answer any questions you have. But next week, August 31st, same time, we'll be having the follow-up session for this. So for now, that's it. Thank you very much, and I hope to see you next week.